All right, cryptography lecture 2. And yesterday we learned a little bit about the greatest common divisor of two numbers and the Euclidean algorithm. To compute the GCD of two numbers, A and B, we call that D, and to write D in the form AU plus BV for UV integers. So just as a kind of review, let's start. This is 1.9a in the exercises. We want to compute the GCD of 291 and 252. So we do successive long divisions. Divide 291 by 252, that goes in one time, and leaves a remainder, I think, of 39. If you divide 252 by 39, that probably goes in 6 times, and I think that leaves a remainder of 18. You divide 39 by 18, that goes in 2 times and leaves a remainder of 3. And if you divide 18 by 3, that goes in 6 times and leaves a remainder of 0. So the last positive remainder is 3, and that's the greatest common divisor of these two numbers. And if we want to write 291 and 252 as a linear if we want to write 3 as a linear combination with integer coefficients of these two integers, we just work the Euclidean algorithm backwards. So 3 is 39 minus 18 times 2. And that's 39 minus, 18 from this equation is 252 minus 39 times 6 times 2. So this is 39 plus 12 times 39. That's 39 times 3 minus 252 times 2. And 39 is 291 minus 252 minus 252 times 2. So if this is correct, and I don't think it is, so let me see where I made a mistake. So 3 is 39 minus 18 times 2. 18 is 252 minus 39 times 6. So that's 39 times 1 plus 39 times 12. That's 39 times 13. Minus 252 times 2. And 39 is 291 minus 252 times 13 minus 252 times 2. So this is 291 times 13 minus 252, 2 times 13 and 2 times 15. So this is AU BV. It was actually 291 times 13 plus 252 times minus 15. So if A is 291 and B is 252, then the U and the V in this equation are 13 and minus 52. So hopefully I didn't make any mistakes, and if you check the arithmetic, should be okay. So that was the first thing we did. This is, and then this was section 1.2, I think. And then the second thing we did, section 1.3, is modular arithmetic. We have a modulus M, and we say that A is congruent to B mod M if M divides A minus B. So this is the relation of congruence modulo M. And we showed how congruences have their own kind of arithmetic. You can add and subtract congruences, and you can multiply congruences, and so forth. So, so M is always a positive integer. So every integer A is congruent modulo M to a unique integer in the set of the first M non-negative integers, which we write as Z mod MZ. This is read as Z mod MZ, if you want to like sort of write it out in notes. And in particular, the congruence AX congruent to 1 mod M. So given a modulus M and an integer A, there exists an X that solves this equation or this congruence. This is solvable if and only if the greatest common divisor of A and M is 1. And that is a basic result. And in fact, we let Z mod MZ star be the set of all numbers A in Z mod MZ, such that the GCD of A and M is 1, and what is called the Euler phi function, phi of M, is the cardinality, the number of elements in Z mod MZ star. So for example, if we take M equal to 10, Z mod 10Z are the non-negative integers from 0 to 9. There are 10 of them. Z mod 10Z star are the numbers in this set that are relatively prime to 10. That's 1, 3, 7, and 9. So phi of 10 is the number of elements in this set, which is equal to 4. So let's move forward. Forward means section 1.4, on prime numbers and what are called finite fields. So an integer P is prime if P is at least 2, and the only positive divisors of P are 1 and P. So if we want to list the first prime numbers, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, and so forth. There seem to be a lot of numbers. An integer n is composite if n is greater than or equal to 2 and not prime. So the first composite numbers are 4, 6, 8, 9, 10, 12, 14, 15, 16, 18, 20, and so forth. And n equal 1 is not prime and not composite. It's the number 1. $101 is prime. 1001 is composite. You can't tell by looking what's prime and what's composite. I mean, because if a number ends in an even integer, it's even, so it's divisible by 2. But for an odd number, it's never always so clear. How do you know this is prime? You have to check. How do you know this is not prime? You have to check. And I think this divides into 7 times 11 times 13. Have to check that first. And prime numbers were studied at length in Euclid. It's not modern mathematics in any sense, but they're questions that Euclid couldn't solve. And for 2,500 years, mathematicians have been trying to solve these questions and failed. So there are lots of simple questions about primes, whose answers we don't know. But a basic fact, which is usually called Euclid's lemma, in the text, this is proposition 1.20. It says if P is prime and P divides the product AB, then it has to divide at least one of the 2 factors. P divides A or P divides B. Or is always the non-exclusive or, it means one or the other of both. So how do we prove this? So suppose we let G be the greatest common divisor of A and P. So G divides P, and the only divisors of P are 1 and P, so either G equals 1 or G equals P. If G equals P, then G is a divisor of A, which is the same as P divides A, and we're done. If G is 1, then the greatest common divisor of A and P is 1. So we can write, so that means that there are integers U and V, this is a set of integers, such that AU plus PV is 1, because the greatest common divisor is always an integral linear combination of the 2 numbers. So if A and P are relatively prime, 1's an integral linear combination. Multiply this equation by B. Get ABU equals PBV plus PBV equals B. But P divides AB, which means AB is P times some number W. So this equation becomes AB is PWU plus PBV equals B. I can factor a P out of this. This is P times WU plus BV equals B. And what does this say? This says B is P times something. So P divides B. So if P doesn't divide A, it divides B. That's a very, very, very nice proof. And more generally, so you can generalize this. If P divides a product of n integers, then P has to divide at least one of them. P divides A sub I for some I. And actually, let me give a proof of this because it's a nice exercise in mathematical induction. So what I want to prove is if P divides A1 up to AN, then P divides AI for some I. So this is certainly true for n equal 1. For n equals 1, this says that P divides A1 implies P divides A1, which is sort of trivial. It's also true for n equal 2. If P divides A1, A2, then P divides A1 or P divides A2. We just proved that. We used A and B instead of A1 and A2. So that's true. So by mathematical induction, we assume the statement is true for some integer n, at least 2. We must prove this for n plus 1. So let P divide A1, A2, AN plus 1. This is a product of n plus 1 numbers. So P divides this. So in particular, P divides the product A1, A2 up to AN times AN plus 1. It divides this times this. That's the same as that. But this is a product of 2 numbers. This is one number and this is another number. And since this statement is true for 2 numbers, that means that either P divides AN plus 1, in which case we're done, or P divides A1 up to AN. But in that case, P divides AI for some I between 1 and n, because the statement is true for P dividing a product of n integers. And those are the 2 cases. P divides this times this. It either divides AN plus 1, or it divides this product of n numbers, which means it divides one of the numbers. So that's an example of a proof by mathematical induction. Okay. And the fundamental theorem of arithmetic, FTA. The fundamental theorem of arithmetic says that A greater than or equal to 2 be an integer, then A is a product of prime numbers. And I can collect the primes, so it's P1 to the power E1, P2 to the E2, P sub R to the E sub R. So this is a product of primes. If I write, for example, 108 is 108. It's 2 to some power times 3 to a power, 27, 50. 2 squared times 3 cubed. So if you don't like this as a product of primes, this is 2 times 2 times 3 times 3 times 3. but I can collect the primes, and so I just write it as a prime power. So the fundamental theorem of arithmetic says, first, every number is a product of primes, and second, that this is unique up to order. By up to order, I mean 6 is 2 times 3. It's also 3 times 2. I have the same primes occurring the same number of times. The only difference is the order in which I wrote down the primes. So up to the order, this is the unique representation of 6 as a product of primes. So to prove, so this fundamental theorem of arithmetic has an existence and a uniqueness statement. The first statement is existence. For every number a, there exists a product of primes such that a is that product of primes. The uniqueness is that up to order, the primes are unique. So how do we prove existence? Well, 2 is 2. 3 is 3. 4 is 2 times 2. 5 is 5. 6 is 2 times 3. 7 is 7. 8 is 2 times 2 times 2. 9 is 3 times 3. 10 is 2 times 5. I mean, you can see every number from 2 to 10 is a product of primes. So suppose every integer m less than or equal to n is a product of primes. Consider n plus 1. I have to show n plus 1 is a product of primes. Well, there are 2 cases. Every integer of these 2 is either prime or a composite. If it's prime, n plus 1 is a prime p, and we're done. If it's composite, n plus 1 is a product of 2 numbers, m1, m2, where m1 and m2 are both less than n plus 1. m1 and m2 are both less than or equal to n. But the induction assumption was that every number less than or equal to n is a product of primes. So m1 is some p1 up to pk, and m2 is some pk plus 1 up to a piece of L. So n plus 1, which is m1, m2, is p1 up to pk, pk plus 1 up to piece of L. This is some product of primes. The primes aren't necessarily distinct or in any particular order. But this is a proof that every number is a product of primes. The hard thing is to show uniqueness, or the harder thing. So how do we prove uniqueness? Of prime factorizations. So suppose A is some product of S primes and also some product of T primes. In no particular order, and the primes aren't necessarily distinct. And that doesn't necessarily equal T. So from A equal P1, P2 up to P3, we see P1 divides A. Because A is P1 times something. So P1 divides Q1 up to QT. But we just proved that if a prime divides a product of numbers, it divides one of the factors. So P1 divides Q sub j for some j. Suppose j equal to t. So P1 divides QT. But QT is prime. So its only divisors are 1 in itself. And P1 is in 1 because it's a prime. So P1, actually, Let's say J is equal to 1. So P1 equals Q1. So in this expression, I can cancel the P1. And therefore, P2 up to P sub S is Q2 up to Q sub T. And this is equal to A over P1, which is less than A. So I can prove either by induction, if this were a statement were true for every number less than A over P1 is less than A, so these are the same primes in possibly a different order. Or I could just say P2 divides this product, it's equal to one of the factors, you can cancel the P2. And you can just cancel everything step by step by step until you get one as a product of primes, so that's an empty product in your products. So you can finish this proof in any one of a couple of different. And that is the very famous fundamental theorem of arithmetic. So if you have a number A, you can write it always as a product of primes, which means you can write it as primes to certain powers. You can actually write it as a product over all primes P, because P to the 0 is 1. So this is P to some power, and power is sometimes called the order of A to base P. So, for example, when I had 108 is 2 squared, 3 cubed. This is the same as 2 squared, 3 cubed, 5 to the 0, 7 to the 0, and so forth forever. This is a product over all primes P, P to the order of 108 to the base P, where the power of 2, the order of 108 to the prime 2 is 2, the order of 108 to the prime 3 in this case is 3, and the order of P to the prime of order of 108 to the prime P is 0 for all P bigger than 3. So this is just a kind of a standard notation for writing prime numbers. No. Remember, we were looking at m is a positive integer, z mod mz is a set of integers from 0 to m minus 1. And the important case, or the most important case, is when m is a prime number p. So in that case, z mod pz is 0, 1, 2, up to p minus 1. And recall that ax is congruent to 1 mod p is solvable if and only if the greatest common divisor of a and p is 1. Well, 0 and p have greatest common divisor p. It's not 1. But if a is between 1 and p minus 1, a is not divisible by p. It's not big enough. So then the GCD of a and p is 1. So for every a not congruent to 0 mod p, we can solve this congruence. There exists an integer b such that ab is congruent to 1 mod p. And we write b is a inverse mod p. Because it's like the inverse of a, I mean, a is like, if these were numbers, the inverse of 3 is a third, 3 to the minus 1. So we said that a is a unit and its inverse is denoted a inverse. Let's do an example. If P is 7, Z mod 7Z. This is all the numbers from 1 to 6. What are the inverses? 1 times 1 is congruent to 1 mod 7. So the inverse of 1 is 1. 2 times 4 is 8, is congruent to 1 mod 7. So the inverse of 2 is 4. 3 times 5 is congruent to 1 mod 7. So the inverse of 3 is 5. Of course, this also says 4 times 2 is congruent to 1 mod 7. So the inverse of 4 is 2. This says 5 times 3 is congruent to 1 mod 7. So the inverse of 5 is 3. And 6 times 6 is 36, minus 1 is 35 divisible by 7. So 6 times 6 is 1. So the inverse of 6 is 6 mod 7. So that is a table of the inverses of the non-zero elements mod 7, the units mod 7. I hope this doesn't seem too abstract, because the world's most important cryptographic system for the last 50 years has been something called the RSA crypto system. And it's based 100% on these facts from elementary number theory, as you'll see maybe tomorrow. Let's see, what's a way to find an inverse? That's kind of interesting. If you like computing, you could turn this into a computer program, if you like. So what is historically one of the great theorems in number theory is due to the French mathematician Pierre de Fermat, sometimes called Fermat's little theorem, which says the following. P is a prime, A is an integer. So there's one statement that's obvious. If P divides A, then A to any power, in particular the P minus first power, is divisible by P. So this is congruent to 0 by P. If P does not divide A, so the greatest common divisor of A and P is 1, then A to the P minus 1, by a miracle, is always congruent to 1 mod P. So for example, if you take P equals 7 and A equal 2, let's see. A to the P minus 1 is 2 to the 7 minus 1, which is 2 to the 6th, which is 64. And 64 minus 1 is 63, which is divisible by 7. This is congruent to 1 mod 7. If you take A equals 3, 3 to the P minus 1 is 3 to the 6th. Let's see, what is 3 to the 6th? The powers of 3, 3, 9, 27, 81, 243, 729. 729 minus 1 is 728. Divide that by 7, that goes in 104 times. So 3 to the 6th is congruent to 1 mod 7. What about A to the 6th? So 6 to the 6th by Fermat's theorem. I don't even want to calculate this, because if I'm doing it by hand, it'll take a minute or two. This is congruent to 1 mod 7. If you take 23 to the 36th power, that's a big number. That's congruent to 1 mod 37. This is simply a to the p minus 1 with a equal to 23 and the prime p equal 37. I mean, to prove this, you can do this on a computer without any trouble, I think. It's actually a pretty big number. I don't know. Depends if your computer can do exactly arithmetic for numbers this big. Probably it's not that big. These are all examples of Fermat's little theorem. And let's see if we can prove this. So if you've taken 314 algebra, you might be able to put together a proof using group theory. But let's see if we can find a proof just using the elementary theory, elementary number theory that we developed. So P is prime, and A is an integer with the GCD of A and P equal to 1. So we can look at the numbers A, 1 times A, which is 1 times A, 2 times A, 3A, 4A, 5A, up to P minus 1 times A. So we have P minus 1 integers on this list. And I claim that if you take 2 different integers on this list, so actually the book uses J and K. So if you take 2 different numbers, J and K, between 1 and P minus 1, then I claim J times A is not congruent to K times A mod P. Why? If JA is congruent to KA mod P, then P divides the difference, KA minus JA, which is K minus J times A. So P divides this, but this is a product of 2 numbers. So this means either P divides, what this vertical line means, K minus J, or P divides A. But we know P doesn't divide A. We chose A that it was not divisible by P. And what about K minus J? Well, K and J are numbers between 1 and P minus 1. So K minus J, if they're different, bigger than 1 and less than, greater than or equal to 1, it's bigger than 0 because they're different. And they're less than P minus 1. So this is a number between 1 and P minus 1. It's not a multiple of P. So P doesn't divide K minus J. So these P minus 1 numbers are distinct modulo P. And every one of these numbers is congruent to something in the set of numbers from 0 to P minus 1. But none of these is divisible by 0, or congruent to 0 mod P. So these are all congruent to something between 1 and P minus 1. And so they have to be different. So every one of these numbers is congruent to one of these numbers mod P. So how can I say this? So for all k between 1 and p minus 1, there exists something, I'll call it r sub k, between 1 and p minus 1, such that ka is congruent to r sub k mod p. So each of these numbers, let me draw sort of a picture if I can. I start off with the numbers 1, 2, 3 up to p minus 1. And I also have the numbers a, 2a, 3a up to p minus 1 times a. Here's ka, but each of these numbers is congruent to a different one of these. So ka is congruent to some number r sub k. And there's some one-to-one correspondence between these numbers and these numbers. So if I take the product of all of these numbers, a1, a, 2a, 3a, up to p minus 1a, that's congruent mod p to the product of all these numbers. Each of these is congruent to exactly one of these, so the product of these numbers, mod p, is congruent to this product. But you see, in this product, I have a occurring p minus 1 times 1 times 2 times 3 up to p minus 1. And that's congruent to 1 times 2 times 3 up to p minus 1 mod p. So that means p divides the difference of these two numbers. A to the p minus 1 times 2 times 3 up to p minus 1 minus 1 times 2 times 3 up to p minus 1. What is that? That's a to the p minus 1 minus 1 times 1 times 2 times 3 up to p minus 1. And this is divisible by p. So p divides the product of these two numbers. But p is a prime. It doesn't divide any one of these numbers, 1 to p minus 1. These are too small. So p does not divide the product of these numbers up to p minus 1, which you could also write, if you like, as p minus 1 factorial. So p does divide a to the p minus 1, which means a to the p minus 1 is congruent to 1 mod p. And that is the theorem we wanted to prove. That's Fermat's little theorem. So as in the example the book gives, because it likes big numbers, in cryptography, you have to use very big numbers. You can't do things without a computer. So it turns out that the number 1548 5863, it's not that big, 15,485,863 is prime. And 2 and p are relatively prime. So 2 to the p minus 1, 2 to the power 15,485,862 is congruent to 1 mod 15,485,863. So without doing any computing, if you take this number minus 1, it's divisible by this. You can also make an observation. If a to the p minus 1 is congruent to 1 mod p, whenever a and p are relatively prime, if we multiply by a inverse, we get a to the p minus 2 is congruent to a inverse mod p. So I don't know that this is a particularly efficient way to do anything, but this is a formula for the inverse of a mod p. By the way, there is a business of finding large prime numbers. It's actually hard to find prime numbers. And suppose you take the number m to be 15,485,207. And we ask, is m prime? So if you compute 2 to the m minus 1, that's 2 to the power of 15,485,206. It turns out this is congruent to 4,136,685 mod 15,485,207, which means it's not congruent to 1 mod m, modulo this. Therefore, m, 15,485,207, is composite. Because if it were prime, 2 to the power m minus 1 would be 1 mod m, and it's not. So you have a way to, when it works, determine if a number fails to be prime, whether a number is composite. And in fact, we know that it's composite, but we don't know how to factor it, which is also quite interesting. Factoring a number, if you have a computer, factoring a number is a hard problem. You might think in Maple, if you use iFactor, you can put in a big number and the computer gives you the prime factors right away. But you're really only using relatively small numbers. There is no computer program known to man or woman or to anyone on the earth that can factor a large number into prime factors quickly. Quickly means in less than 100 million years, let's say. Now, a lot of this, if you've taken algebra, should remind you of algebra, but I don't assume that you've taken algebra, so it's kind of irrelevant. Suppose P is a prime and the GCD of A and P is 1. So we know that by Fermat's little theorem, A to the P minus 1 is congruent to 1 mod P. So for example, if we take A equal 2 and P equals 7, 2 to the 6th, which is 64, is congruent to 1 mod 7. But also 2 cubed is congruent to 1 mod 7, because 2 cubed minus 1 is 8 minus 1 is 7 times 1. Here, 2 to the 6th minus 1, 64 minus 1 is 63, which is 7 times 9. So 2 to the 6th is congruent to 1 mod 7, but there's a smaller power of 2, which is also congruent to 1 mod 7, namely 3. And we say that the order of A modulo P, where P is a prime and A is an integer relatively prime to P or not divisible by P, is the smallest k, positive integer k, such that a to the k is congruent to 1 mod p. And what we know is that this k, so most p minus 1, at least 1, so, but it doesn't have to be p minus 1. Here's an example where the order of 2 mod 7 is 3. And we have the following proposition. Again, P is prime. The GCD of A and P is 1. Suppose that the order of A mod P is K. If n is any positive integer or any integer, if a to the n is congruent to 1 mod p, then k divides n. And the proof of this goes as follows. Suppose we take n and divide by k. So n is k times quotient q plus r. R is between 0 and k minus 1. So a to the n is a to the kq plus r. That's a to the kq times a to the r. A to the kq is a to the k to the q. This is just ordinary arithmetic. But a to the k is congruent to 1 mod p. So this is congruent to 1 to the q times a to the r mod p, which is congruent to a to the r mod p. And we're assuming a to the n is congruent to 1 mod p. So a to the r is congruent to 1 mod p, but r is a number smaller than k, so most k minus 1. But k is the smallest positive integer, which satisfies this congruence. And r is smaller than k, so r cannot be a positive integer, so it has to be 0. 0 is not positive. R is 0 means k divides n. And that's what we wanted to prove. Again, all of this is written out, let's say, neatly in the text. That's important. Okay, and there's one final theorem about congruences that I'm going to state, but I'm not going to prove it because it takes a little bit more work than we have time for. So the book takes the same approach. So this is in the text, theorem 1.31. And I'm going to give it a star because it's so important. It says the following, that P be a prime number there exists a number G in Z mod PZ star, which is with the positive integers from 1 to P minus 1, such that the powers of G, let me say in 2 ways. If the GCD of A and P is 1, then there is a K such that K is between 0 and P minus 2. G to the K is congruent to A mod P. In other words, every integer a from 1 to p minus 1 is a power of g modulo p. And g is called a primitive root. Modulo p. So for example, if I take p equals 7, g equal 2 is a primitive root. So what are the powers of 2? I have 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the fourth, 2 to the fifth. What are these numbers? This is 1, 2, 4, 8, 16, 32. But, doesn't work. So 8 is the same as 1. 16 modulo 7 is 2, and 32 mod 7 is 4. So the powers of 2, the powers of 2 to the k mod 7 are just 1, 2, and 4. We don't get all the numbers, 1, 2, 3, 4, 5, and 6. So g equal 2 is not a primitive root mod 7. Let's try g equal 3. So we have the powers 3 to the 0, 3 to the first, 3 to the second, 3 cubed, 3 to the fourth, 3 to the fifth. 3 to the 0th power is 1, 3 to the first, and I'll compute these things, mod 7. 3 to the 0 is 1, 3 to the first power is 3, 3 squared is 9, which is 2 mod 7. So this is, let's say 9 is congruent to 2. 3 cubed is 27, which is congruent to 6 mod 7. 3 to the fourth is 81, which is congruent to 4 mod 7. 3 to the fifth is 243, which mod 7, 7 into 243 goes 3 times, 7 into 33 is 5. So this is 1, 2, 3, 4, 5, 6. So 3 is a primitive root mod 7. The set of powers, 3 to the 0, 3 to the first, 3 to the second, 3 cubed, 3 to the fourth, 3 to the fifth, mod 7, give us 1, 2, 3, and in some order, 4, 5, and 6. So 3 is a primitive root, mod 7. By the way, for p prime, we write often f sub p as z mod pz. This means the finite field with p elements. Right? Z mod pz has p elements. The integers 0, 1, 2, 3 up to p minus 1. Everything is a unit except 0, and that's how we define the field. You can add, subtract, multiply, and divide by anything different from 0. So Z mod PZ is the finite field with P elements. Just never know. Let's see. Claim 2 is a primitive root modulo 11. Let's check. 2 to the 0 is 1. I have to get all the numbers from 1 to 10 by taking powers of 2. 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. 2 to the fourth is 16, which mod 11 is 5. 2 to the fifth is 32, which mod 11 is 10. 2 to the sixth is 64. Mod 11 is 9. 2 to the seventh is 128. Mod 11 is 7. 2 to the eighth is 256, which mod 11 is 3. And 2 to the ninth is 512, which mod 11 is 6. So if I look at the least non-negative residues of the powers of 2 mod 11, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I get all of the congruence classes, all of the possible numbers mod 11 as powers of 2. And the primitive root theorem says that every prime number has a primitive root. So let me just state this again because it really is a very important fact. Every prime number P has at least one primitive root, we often call G. And finding primitive roots is a hard problem. Hard means a computer can't do it. I mean, a computer can do it eventually, but eventually the sun burns out and the earth doesn't exist anymore. But that's not so good for us. And an ancient problem, if you start looking for primitive roots, you find that the number 2 is often a primitive root. Obviously not always. We saw a counterexample, but is 2 a primitive root for infinitely many prime numbers P? If you solve that problem, you will become famous. I would like actually to go from this to the RSA crypto system, just so you can see an immediate application. So let me find that. So this is in chapter 3. And maybe I will just jump to that right now. It's fun. So chapter 3 is posted on Blackboard. And chapter 3 is called Integer Factorization and RSA. So we studied primes, PQ, and so forth. And now we want to consider numbers that are products of two distinct primes.
Excuse me, Professor. So let's say we go from chapter 1 to chapter 3 now, in terms of like what we're studying. Like we don't really go over too much chapter 2.
Well, no. We're going to go over chapter 2, and we're also going to finish chapter 1. But
Okay.
since I just spent a lot of time developing this number theory, I thought it's interesting to see how this is actually used to create a crypto system.
Okay.
And
Okay.
not one just in theory, but one that's used right now in practice everywhere in the world constantly.
Okay.
So I'm going to go back to chapter 1 and chapter 2, but I'm going to jump ahead just for now to chapter 3.
Okay.
Because it continues the number theory. Okay. So here's a simple problem. This is really the crux of a lot of cryptography. Two problems. I give you P and Q primes. You compute P times Q. Right? How do you do that? Well, you either have a big piece of paper or a computer. Suppose I give you primes, P and Q, and I know they're primes somehow, and they each have like 1,000 digits. And I tell you to multiply them. And your computer can do that really, really, really fast, right? So this is problem 1. So I give you P and Q, you give me the product. Here's a different problem. I give you a number n. And I tell you that n is the product of two primes, P and Q. That is, I don't tell you what the primes are. I tell you that n is P times Q. Problem, factor n, and give me P and Q. Okay? So these are sort of like symmetric problems. In the first problem, I give you two primes, and I ask you to find the product of the two primes. In the second problem, I give you the product of two primes, and I ask you to factor it and give me the two primes. So problem 1 is easy, right? I mean, it's easy for a computer. Problem 2 is, at the current state of knowledge, impossible. Now, you might say, how can it be impossible? Because if you give me a number, I can ask the computer to divide it by 2, 3, 4, 5. Just keep dividing it by numbers until you find a factor. And if the number is a product of two primes, that factor has to be a prime, and the quotient is the other prime. So this is clearly a computable problem. So what does it mean to say it's impossible? What it means to say it's impossible is your computer, if the number is big and you're doing all these trial divisions, like you'll die and the earth will disappear and the sun will burn out before you finished all these trial divisions. It just can't be done in, thousands and thousands and thousands of years. If you're doing brute force computation, just dividing by successive numbers until you find a factor, it's not going to happen. If the numbers are big, it can't be done efficiently. Now, if you follow these things, one reason for the interest in quantum computers is, in principle at least, there's a quantum computer algorithm that can factor a number that's a product of two primes. So if quantum computers could ever be made to exist, right now they're all fairly trivial. They only can do very little work. If you could make a quantum computer, you could factor a number, and you could break all the crypto systems that are used now by the military, by international banks, by Amazon, by everyone. Because everything is based, almost everything, is based on the fact there's no way to factor a number in a reasonable amount of time. And given that difficulty, that's what makes this RSA crypto system work. So let's see, what is an example? Well, let's see if we can start a little bit as follows. We know that Fermat's little theorem says that if P is prime and the greatest common divisor of A and P is 1, then A to the P minus 1 is congruent to 1 mod P. Then there is a generalization of this, which is called Euler's theorem, spelled E-U-L-E-R, which says that if M is just a positive integer, and the greatest common divisor of A and M is 1, and phi of M is the Euler phi function, which is the number of units in Z mod MZ, the number of numbers from 1 to M that are relatively prime to M, then A to the phi of M is congruent to 1 mod M. And if P is prime, phi of P is always P minus 1, so we recover Fermat's little theorem. So Fermat's theorem is a special case of Euler's theorem. And we're interested in a special case of Euler's theorem, which is when M is a product, P times Q, a product of two primes. So P and Q are distinct primes. And in that case, phi of M turns out to be P minus 1 times Q minus 1. And so in that case, for a modulus, which is a product of two distinct primes, if A and PQ, so if A is a number not divisible by P or Q, then A to the power P minus 1 Q minus 1 is congruent to 1 modulo PQ. In fact, sorry. Yeah, so this is certainly true. Something stronger is true. And that's going to take a little bit more time to. Okay. Yeah, I mean, this I can't do in 10 or 15 minutes. I'm going to stop at this point and I'll continue tomorrow. But I do want to digress from going through the book in linear order, chapters 1, 2, 3, 4, 5, and so forth, because I do want to explain this RSA crypto system, and I'll continue with this tomorrow. I might have to adjust the homework a little bit to fit the fact that I'm putting this in at this point. Okay.
Okay, thank you.
Yeah. Any questions before we stop?
Quick question, Professor. I know our midterm is next week. If
Yes.
you did make a review, would it be posted like sometime this weekend or?
No, no way. Because that would only cover, by this weekend, we've only covered half the material. And there's a lot of, I mean, there's a lot to do.
Yeah, because isn't our midterm exam like next Friday or
No,
something?
Thursday.
Next Thursday, right? So
Right.
let's say,
So
like,
think
I don't know.
like this.
Mhm.
Each week we cover a month of material.
Mm-hmm.
So next week, there's a whole month of material we haven't talked about yet.
Yeah.
But I can't put together something, but it might just be
The homeworks or
the
something like.
homework problems, basically. But I will try. I will try to put together something this weekend.
Okay. And Professor, another question. In terms of like the questions for the exam, like are they going to be similar to like the homework? Or are they going to be like or are the exams already created for you type thing? Like and you don't know what's on them.
Well, no. There's nothing that makes exams for me. I wish there
Okay.
were, but
Yeah, so like the depart because I know like with some professors like the department just like gives them like some exams and some professors they don't make their own, but
that's
so
only
yours.
in like the beginning classes, like calculus 1 and 2.
Oh, okay.
I don't think it goes anywhere beyond that.
Okay. So let's say so basically at least like if we want to start studying now like this like beginning like chapter 1 and stuff like that, start like reviewing the homeworks and stuff like that and doing them to prepare for the midterm.
Right. Well, it is going to be chapters 1 and 2 plus RSA,
Okay.
because there's a lot in chapter 1 I haven't covered yet.
All right. Yeah, because I think let's say we're up to chapter what's a 1.5 right now, right?
Yes.
We went through. Okay.
Yeah. Okay.
All right. That's
All right. Be back tomorrow.
Thank you.
Bye.